Okay, so I'm going to talk about basically a case study and integration that we did of some existing Collins flight vehicle mission software on seL4. This was part of the DARPA PROVERS program that John gave us a nice intro to this morning. But first, by way of background, and this also connects very much to Boyd's sermon, this is kind of a bright spot, I would say. If you haven't looked at it, hopefully maybe you have, but DARPA is actually, for the last year or so, really leaning into this challenge of how do we get formal methods, automated reasoning, adopted by especially defense system developers. So DARPA has been supporting the development of formal methods tools over at least the past 15 years, and in some cases, there's instances beyond that. We've been involved with them for most of that time. But they have what they're calling now their resilient software systems thrust. There's been a number of meetings and requests for information and things in an upcoming program in this area. But the goal is really to accelerate the adoption of formal methods to improve the cyber resiliency of national security and defense systems by eliminating cyber vulnerabilities. And they're trying to, they're conducted a number of different activities to try to actually do this and gain evidence of, what did you do, how much did it cost, what improvements did you make, to be able to communicate that to their customers, who are the branches of the U.S. Department of Defense. So they're actively engaged with the Army and the Navy and the Air Force to identify systems where they can actually do these kinds of demonstrations. And in fact, if you go to the DARPA webpage and look around a little bit, you will find a formal methods page. It has a lot of interesting history and information for current and past programs. Happens to mention as a case study the HACMS program that a number of people in this room were involved in, and also highlights seL4 as an example that you should be aware of how to use and extract benefits from formal methods. And they've even got this guy, Emil Michael, giving a short talk about the nature of the threat that we face right now, and how formal methods are going to be a key part of addressing that threat. So this guy is DARPA's boss, and he is saying, threat is imminent, and we have to use formal methods to address it. Okay, so shame on us if we can't, get some traction and biology make some progress in this environment. So one of the programs that is affiliated with this Resilient Software Systems Thrust is the PROVERS program. Its stated goals are to develop automated, scalable formal methods tools that can be integrated into traditional software development pipelines, enabling traditional software developers to produce and maintain defense systems. And by traditional here, what they mean is people that work at my company, defense and aerospace contractors, not trained formal methods people, but software engineers or craftsmen, to be able to make use of, take advantage of, exploit the benefits of formal methods. So, and part of selling this program was, hey, a lot of these kinds of companies are doing this now successfully. Why are not these kind of companies also doing this? Okay, so this is kind of the background, the goals of the PROVERS program. So we're leading a big piece of the PROVERS program. Here are all of our teammates on this. So we've got CMU, University of Kansas, Kansas State University, UNSW, Proofcraft, and DornaWorks, many of which are here today. So I talked about this last year, but this is kind of a reminder of the bigger picture of our piece of the PROVERS program called INSPECTA. And really, we're developing formal methods tools at every layer of the software stack, developing, improving, integrating largely on this program. So going from requirements and system architecture models through the application code, the infrastructure code, and targeting seL4. So we are, creating, we've got kind of two different transition mechanisms captured here. One is giving engineers tools that they can use integrated with their existing CI/CD pipelines, and also providing access to verified, highly reliable artifacts like the seL4 kernel, making it easier for them to use that without having to recreate that or understand the proofs themselves. So those are two mechanisms: give people highly automated tools that they can use, or give them a verified artifact that they can reuse easily a bunch of times. All right, so we kind of have two types of activities in our program. This outer loop, where we're improving, integrating our tools, and this inner loop, where we have a couple of different platforms that are actually using these tools and demonstrating their effectiveness and giving us feedback to improve the tools. And here's just an example of, we have an assurance dashboard that's part of our CI/CD pipeline that gives you, just like if you were running a regression suite, giving you updates on what tests are passing or failing. Same thing with, we're running Virus and Resilient, which is a kind of a AADL linter tool that we have, and Hammer that John talked about, and all these kinds of things will just be part of the development pipeline. Okay, so our demo platforms. We have an open platform that's being developed and supported by DornaWorks. It's based on just the ArduPilot software kind of at the core of it, and some Rust components that we're building around that to enhance its security, and running seL4, and it's on a Zynq UltraScale platform, the ZCU 102. And Robbie's going to talk about this on Thursday. And so what I'm going to talk about now is our restricted platform. So this is based on the Collins Rapid Edge mission computing software. It provides collaborative autonomy, so multiple vehicles working together to accomplish a mission. It's deployed in small unmanned air vehicles currently under development, and with the ability to support a variety of types of payloads, often surveillance kind of multispectral kind of surveillance payloads. And conveniently, it's based on the same computing hardware family as the open source platform. So we hope to be able to, mock up on the open platform specific examples of architectures that we need, and be able to implement that very easily, bring over onto the restricted platform. So this is the kind of thing that you should have in mind. This is one example of the kinds of vehicles that Rapid Edge has been integrated into. So you have this small UAV wings. You can imagine this being shot out of a tube on the side of a helicopter. Wings fold out and it goes and flies around and collaborates with other similar vehicles commanded by, or at least tasked by, somebody in the helicopter, or it could be launched from a vehicle on the ground. But in this particular one, there's a couple of Collins radios on there for talking to the control station and the other vehicles. There's this tactical guard module, which is doing some crypto and other things. The GPS receiver payloads, and this host compute resource, which is our mission computer, which is running this Rapid Edge autonomy software. And that has inside of it 4 of the Zynq UltraScale MP-SOC chips. So it's got a lot of compute in there. We're not making use of nearly all of that now. So here's a little bit more about Rapid Edge. It is it's This hierarchical autonomy framework was developed by our mission systems business in Collins. And the idea when you use it is that you'll have an operator and they provide high-level mission goals, how to configure the assets, the vehicles, and for example, here are some areas that I want you to go out and do surveillance on and tell me where the targets are in there and try not to get shot while you're doing it. And 3 vehicles are going to go and you guys figure out how to divide up the area. So just kind of giving this high-level tasking, and then the Rapid Edge software figures out and does the coordination and sends guidance commands to a flight computer on the vehicle. So this is a very high-level view of the kinds of things that are inside of the Rapid Edge software. It's based on the MOSA, Modular Open Systems Approach architecture that the military has been developing and standardizing, has standardized interfaces. It consists of a bunch of individual services that are pretty loosely coupled. That has some advantages for us, as we'll see in a minute. Also, everything just communicates over network interface. So all of the sensor data is coming over regular, IP protocol, and it's sending its commands to the autopilot using the network. Can run on ARM or x86 architectures. Can deploy it as a Docker container or without containerization, so it's pretty light on dependencies. It's intended to be scalable and easy to run on most any platforms. We have this running on vehicles that look like the one I showed in the picture before, but also on little quadcopters, on the Saxon Monitor UAVs that we've used for some flight demos. So you can run it on like a Raspberry Pi. It's pretty, pretty platform independent. So in our demo that we did at the end of phase 1 of the PROVERS program, so it was in March of this year, we did this. We wanted to get just an early integration to just show we were on the right track and things were gonna work for the rest of our program. So nothing fancy here. We just took the Rapid Edge software, deployed it as a Linux VM on seL4 on the ZCU 102 platform, and showed that we were able to successfully execute the software without any changes, no mods to the existing software, running in its VM in our simulation environment at Collins, and replicated some previous flight tests that we had done, kind of setting the stage for further use of formal methods in the rest of the program. Okay, so a few challenges and simplifications that we made along the way. So it is likely that we were going to do this on the flight hardware that has been in development for the Army. That's expected to change in the next year or so. So rather than spend a lot of time on that, we decided to just go ahead and target the ZCU 102 for the demo. Same board as we're using for our open platform, and then we'll port to the new flight hardware whenever it's available. Secondly, this Rapid Edge software currently, it requires it's running on a that has ARM A53 cores on it. We're running on multiple of those cores to get the desired performance, and right now we don't have the all of the things that we were doing are just running in single core mode. So rather than deal with that immediately, we decided to split the Rapid Edge code into multiple VMs, and just run one of them on one of the cores. because that was sufficient to accomplish our goals for this initial integration. That ended up being very straightforward because of the way Rapid Edge is architected, just as this collection of services, so it was that talk over the network, so it was easy for us to bundle that as a couple of different VMs and then run one in the on part of our simulation environment and one actually on the target hardware. And then, coming back to the multi-core issue, multi-kernel support for seL4, still under development. I know Gernot, yes, we have multi-core support SMP, but there's not going to be a verification story for that within the scope of the program. So our preferred solution will be a multi-kernel configuration, which is not yet supported on MicroKit, which is what all of our tools are built on. So again, for purposes of this demo, we just stuck with the single core implementation, and then as soon as we have multi-kernel on MicroKit, then we'll switch over to that and bring this other VM back onto one of the other cores. Okay, so this is just what I was telling you. We split the Rapid Edge software into a couple of different VMs. So in our this is what it looks like in the lab in Cedar Rapids. So we have kind of in the on the middle shelf there is the ZCU 102 board, and then a laptop on the bottom. So in this virtual system integration lab, we have a bunch of stuff that's just running in software anyway, right? So we have the environment, the other vehicles, the payloads, and so we just added to that the other Rapid Edge applications that didn't fit on the one core, and then the one VM that we care about running on a Linux guest OS and VM on the ZCU 102. Okay. So this is a press release from last year. We did a flight demo at the Army Edge 24 event on the desert. This is at the Saxon Monitor UAV that I mentioned. So this one actually has wheels on it, so you can take off and land. That other one I showed you in the picture, that was clearly an expendable type of vehicle because it has no wheels on it. Yeah, so we had a couple of these that we went and actually flew around on some simulated missions, demonstrated the capabilities of the Rapid Edge collaborative mission autonomy software. So our goal in this exercise in Provers was to replicate one of those missions in the lab, but with seL4 hosting the Rapid Edge software. So here you're going to see vehicle one, the kind of brighter one on the right here is the Rapid Edge running on seL4 in the hardware in the loop on the ZCU 102. Vehicle 2 is in the VSIL. And you can see they go off and they are orbiting around, taking pictures or whatever they do. Kind of each one of the areas that you see them orbiting in is an area that they've been tasked to go and get, look for targets and get surveillance data. So here now they're doing the second area. They'll fly around, and when they're done with that, they'll move off into do the third area. And there they go. All right. So if you can squint, you can kind of tell here on the left is the 2024 flight test, the tracks that the two vehicles took, and in replicating this, we inadvertently switched the colors, so the aqua is the blue and the blue is the aqua. But you can kind of see the circles where they orbited are all in the same place, so that in our seL4 demo, we showed them doing the same thing as what they did in their actual flight demo, which was the point. Okay, so even though this is a very basic initial demo, there are some security benefits, right? The Rapid Edge software was not designed with any cybersecurity considerations. It was really focused on the autonomy capability because that's what the customer was looking for. So even already we've made some improvements by putting this thing in a VM where we've reduced the attack surface to one. It has only one interface to it, just a network interface. Everything goes through that. So anything else, any ports or anything else that might have been accidentally left open or any other ways that you might try to attack this thing have been closed off just by sticking it in a VM and locking down the interface to that. And this is very similar to what we've done on the open source platform as well. And then we have strong isolation between that and anything else that we choose to add to the system going forward, which I'll talk about next. And this mode here is something that we've seen as a common usage pattern, taking legacy software, existing software that we really don't have the resources or the need or the intent to rewrite to run natively on seL4. We can put that into a VM and at least protect that so that we know it's not going to influence other parts of the system in any ways that we don't intend for, or conversely be influenced by other things, other entities that might try to attack it. Some next steps going forward. Obviously, we'll add multi-kernel support as soon as we can, so we'll have probably 3 of the cores dedicated to running different parts of the Rapid Edge software, and then a 4th core that will dedicate to some new security functions and firewalls and things like that. This initial version was built on camp keys. We'll switch over to MicroKit for that. It was also built manually. One of our next steps then will be having the engineers that built this use the rest of the INSPECTA tool stack, like John was illustrating in the talk this morning, in order to create a model of the system and then generate all the code automatically for the deployment. And then eventually we may move to flight hardware as well. And I should mention all of this work that I'm describing was not done by our research organization in Collins. It was done by the Collins Mission Systems engineers. So they were able to, with some minimal hand holding, pick up seL4 and figure out how to, get their code packaged as a VM running successfully on that. So here's just another look of some other things that we will plan to do before the end of the program. We'll add firewalls to manage, to monitor for malformed packets, and then also some other behavior monitors and deep packet inspection capability. Probably add another VM that you can consider like a sandbox for new capabilities that you might want to add to the system in a way that protects it and keeps it from compromising the rest of the system. Concluding, we successfully integrated the Rapid Edge software with seL4, showed that verified that the software works as expected in our hardware-in-the-loop simulation, producing the same flight behavior in the sim that was seen in the flight demo last year, and positioned us for what comes next in the rest of the PROVERS program. Charlie.
I'm curious what issues you think are going to
Yeah, our expectation is that it won't. I mean, it's already running on two completely separate computers, right? And so it just shows you that those services are pretty loosely coupled anyway. This isn't an especially real-time system, except for the fact that it needs to process the sensor data as it comes in. So it needs to kind of get around to that. So it's got data coming in at 10 or 20 hertz, depending on the source. And then it's sending out targets to the autopilot, but those don't have to go out at a regular, it's not wiggling control surfaces itself, it's just sending targets and turn radius and other information, higher level information to the flight control computer that then itself is real time. And that's a very common architecture and the kind of things that you see deployed today.
Yeah, I guess that was kind of what I was getting at, was like the performance I captured in real time.
Yeah, we just need to get the throughput handling all the messages so they don't back up. Yep. Cool.
Is there any particular difference regarding the beneficial side of SNE versus multi-kernel, or is it basically completely irrelevant for this platform for which one you go?
For this platform, it's pretty irrelevant. In a lot of applications I've seen, we would be perfectly happy with, I mean, having the verification story is a priority, which leads us to prefer the multi-kernel solution here. There's actually some benefits from determinism, having things locked on particular cores. So that's maybe you're giving up some efficiency there, but I think on the whole I prefer the multi-kernel approach. And I'm done.
Just to comment on that one, actually 2 comments.
Yeah, I knew I was not going to get away with
No. So, if you're building on the microkit as they do, then the microkit will pretty much abstract over multi-core versus multi-kernel. The second is, for many platforms, in particular x86, it doesn't actually make sense to run a multi-core version because the cores don't share an L2 cache, and the cache migration latency is bigger than the cost of a system call, so it's basically an insane setup. They are on ARM. They are for small clusters. They share an L2, so performance-wise, it's better to have a multi-core version. But in terms of systems design, it's not a big difference. Any other questions? Okay, so we are done.